Moritz.
Thank you so much, yeah, Friederike, and also Marcus. Very wonderful introduction, I think, for what I wanted to present today, which is kind of my understanding after spending a couple of years trying to push and to grow from thermochemistry, I mean, providing a software provider for thermochemical simulations, to being a software provider maybe for process models. And I learned a lot. I got sometimes a bleedy nose, maybe. I also really liked when you mentioned Harman sitting next to the furnace and feeling the furnace. And I know that I'm lacking this. And as Friederike says, I have a passion for philosophy. So I'm approaching the problem maybe from a slightly different angle. Yeah, but I wanted to share what I understood. To make it maybe also a bit easier to come into discussion, because I also really liked what you pointed out concerning we don't know everything. We are lacking a lot of understanding, and there is a problem of overselling, maybe, very often in academic publications concerning what problems are actually solved by a publication, by some work at university or whatever. Okay. So if you think about the history of process modeling, the history of developing these things that we are using today, the physics understanding that we're using today, I asked ChatGPT, okay, give me a bit of a history, like major milestones that are relevant for metallurgical process models, and that is kind of what I got from that. So for 20 years now, roughly, we have the AI physics-informed models. We have CALPHAD, of course, for 60 years now, but I mean, 60 years was kind of the beginning of CALPHAD, and of course it takes quite a bit of time to actually then get the database parameters that need to go into highly accurate, greetings to Alex, thermochemical database. And of course, it's never perfect. Our job is unfortunately never done. We're working on it. We're also working on making that easier. You will see that later in Florian's talk. And I think it is easier today, and that's also part of our attempt to answer your question, Alex, concerning how do we ensure that more people do the measurements. We try to ensure this by making it easier to digest the measurements and to create the added value of that is generated by a CALPHAD database. Okay, then I'm obviously not an expert in finite element methods. That has been around for roughly 70 years. Then 120 years. Third law of thermodynamics, okay, that's a wonderful one that we use sometimes. But then we have Arrhenius equation, we have Gibbs phase rule, Fick's law, first and second law of thermodynamics. So we're talking about things that have been around for more than 100 years. And we're still using it, it's state of the art, and it's not dead, yeah? We still need all of that. And then we can go even further. If you think about process model, you need transport. And actually, Fourier-Navier-Stokes equation, or the equation is 200 years old. Unfortunately, not really solved. One of the big mathematical problems. But it is understood that is ultimately the fundamental equation that we need to solve in order to get to a process model. And then Newton's law of motion, 340 years, of course, we also use that. And then now really getting to the fundamentals. Heraclitus' interpretation of matter through processes, 2,500 years. Okay, and I want to quickly go back to that time. So if you visit Rome, you will find this wonderful picture of the School of Athens. And there are a number of people here who have published on process models. You should know, of course. Okay, so we have here at the front, we have Heraclitus with his pantarei, everything flows statement. So understanding things by understanding or by watching what is changing. We have Zoroaster, a couple of 1,000 years even earlier, who, and forgive me if I'm completely mispronouncing this, distinguishing Asche and Raj, the truth, the rightfulness, the order, we all like that, enthalpy plays into that one, and the other side, the false or state, and also the disorder, of course. Yeah. Okay, then you find here Democritus with his atomism. Yeah, there are small packages, and then we can stop there. We don't need to go even deeper. I like that thought. And then if we go to the center, we see Plato, who in his wonderful allegory of the cave told us to be very difficult when looking at appearance of a system, and considering that that is just the appearance, it might not be the reality. And there are many models, one reality, also part of how you can interpret his work. And Aristotle, I like the why thing. Simon Sinek says, start with why. Aristotle did it a couple of thousand years ago already. And he said, if you ask why, you can ask for 4 different things. You can ask for a material reason or a material cause. You can ask for a formal cause or an efficient cause, or the final cause. And I will come to that again at the end of the talk. Okay, Ibn Rushd, the interpreter of Aristotle, just a few hundred years ago, he has essentially educated the West that there has been Aristotle and all of those folks before, because that was forgotten in the Middle Ages. I think it's nice to keep that in mind. Reason interprets nature. This is what we're all trying to do, right? We're just trying to follow that. Okay, I want to bring this into a hierarchy, because I think it's important to keep into account that, I mean, you had the picture of a part maybe, and then the ores and all of that, scrap, whatever. Everything at the lowest level that I actually care about, of course we can go deeper, we start with an atom assembly. Or atom assemblage, and that means we have atoms, and these atoms have some positions, right? It's all that simple. Everything around us is like that. And we all probably in physics classes, we went through this example. Let's say 2 atoms, and we want to plot internal energy as a function of distance. And you would find such a potential curve. Yeah, you can calculate such a potential using simple equations, Moritz potential whatsoever. And when you do this, you must keep in mind that you are already doing a coarse-graining, because you're ignoring electronic degrees of freedom, magnetic degrees of freedom, and all of that, right? Okay, now we have 2 atoms. We give them a bit of temperature. The atoms will start vibrating. They will explore the lower part in this basin. And you see now here the blue to red, increase in temperature, you will have more vibrations and all of that. You can build a partition sum. If you have the data, you can build a partition sum, you can evaluate the partition sum, and you will get, you can get something like this with a coarse-graining approach again. You can get a plot of internal energy or Gibbs energy as a function of temperature and also distance, right? So that is something, if you have a Morse potential, you will get this immediately out of it. You're ignoring the exact shape of the Morse potential, but you have properties that are useful to work with as you go up in hierarchy, right? If you do a process model, you don't really care about the potential of 2 atoms, right? Yeah, no, we don't care about that usually. Maybe you do later. In diffusion modeling, we will see that in a few hours, I guess. Okay. Now, this is what we're doing when we're developing phase models. Yeah, we're trying to describe how a phase behaves without going into all the details that are needed to understand how an atom assemblage behaves. I want to go back to the atom assemblage, because that was just 2 atoms, and I know that very few people here care about 2 atoms. We care about n atoms. Ooh, wonderful, n atoms of same type. So these are, if we have n atoms, each atom has 3 coordinates, x, y, z. So if we want to plot now the internal energy as a function of some spatial variable, we have 3n spatial variables because each atom has 3 coordinates. So this is a very, very tough one here, and I'm abstracting away all of the 3n dimensions. I'm replacing by a single dimension. Of course, this is not the reality here, but you will, of course, find some low energy valleys again in this 3n dimensional space. Okay, and we give these valleys, we give them names, we call them body-centered cubic, face-centered cubic, liquid, whatsoever. Yeah. And again, you can do this with atomistic simulations. You can calculate these diagrams if you want to. Again, you're doing a coarse-graining approach concerning electronic degrees of freedom, magnetic degrees of freedom, all of that. Now, is this just Moritz fantasy that this is reality, or is it true? No, it's true. We all know it. Martensite transformation follows the Baben path, and that means that the material is moving from the basin of the FCC phase into the basin of the of the BCC phase, yeah, via a diffusionless transformation. Even the energy hill between the two basins are things that are in reality really, really important. Okay, again, we can build a partition sum here in the basin for the BCC phase, for example, and we can then plot for something that we call BCC iron, where we abstract away all of the 3n dimensional degrees of freedom. We can then plot internal energy and Gibbs energy. And also the lattice parameter of the BCC phase. Yeah? These are things that we use, that we make use of, and all of this is coarse-graining. We ignore all of the details at the lower level. We can do the same for the FCC phase, and then we can see, okay, there's at some temperature there's a phase, or there's an equal Gibbs energy of FCC and BCC, and there you expect then a phase transition. Okay. Again, this is how we move from atom assemblage to the phase level. Yeah? We are ignoring all of the details of crystallography, of whatever goes in there. We are just using this. Okay, now, we don't only care about one atom type, we care about different atom types. Marcus, 15 atoms, 15 atom types in an ore, 30 in an electronic product or something like that in a scrap. So we have to conceptually make that change as well. So we might have an element number 1 that has a energy versus coordination space behavior as shown here, and we have an element number 2 that is more stable in FCC than HCP. And now what we have to do is we have to define a third axis, or a new dimension essentially, going from the pure element 1 to the pure element 2, and then we can follow. We don't want to follow here probably the maxima of the internal energy space, but we will only follow the behavior of the minima in the internal energy space. Yeah? And again, we do this with a coarse-graining approach, and we can then follow how, for example, the minimum of the thing that we call HCP is changing with composition from element 1 to element number 2, and so on and so forth. And we will see that maybe the mu phase, which was not stable at all for the 2 elements, suddenly is stabilized in between the 2 elements. When we do this, we can again do the coarse-graining. We get rid of all of the 3n dimensions of space that are needed for the atom assemblage. And now we have a phase model that describes how the Gibbs energy ultimately of a phase changes with composition, temperature, and pressure. And this is what we're doing with CALPHAD. Yeah, that's all that is done in the CALPHAD database development. We are developing these expressions here, or expressions to describe these curves. All right. Once we're here, just want to point out, we are ignoring the the degrees of freedom in space, the 3n degrees of freedom in space when we do this. Yeah, because in practice, probably all of our customers do not really care about those degrees of freedom. Now, once we have it, we can go up in the hierarchy. once we have phase models, we can get to a diagram like this one, where we can see how phase amounts change as we change, for example, here, the hydrogen to water ratio in a multi-component system. So Anna will talk more about that. The only detail I want you to notice here is that we have a phase label. And look at the curve for the FeO. You see that the FeO is changing mass here in the middle region, and that is why is it changing mass? It's changing mass because it is changing stoichiometry as you change the oxygen partial pressure. We ignore this when we draw this diagram. We ignore the exact composition of the Wüstheit phase. Yeah, we just say, yeah, it's Wüstheit. We have, I don't know, 100 grams of Wüstheit. Yeah? So again, we ignore the phase internal degrees of freedom when we plot things like this. And that's okay. We can do that. Okay. Now we are in the phase assemblage, and now we can move up in hierarchy to the microstructure. What is a microstructure? A microstructure is essentially the phase assemblage plus the information concerning the spatial arrangement of this phase assemblage. And I will not go into that. I know I'm speeding up a bit. In this case, we're ignoring probably again phase intercomposition, maybe crystal structure. Here we are doing the least amount of coarse-graining, I would say, in practice. Yeah, okay, good. And then we can go up in hierarchy. And you have talked a lot about more like mesostructure to macrostructure effects. And every time that we change in hierarchy, Anna will show a nice video later for an iron oxide pellet where you see this change in hierarchy, and every time we do this, we're ignoring, in a way, what is happening at the lower scale. Yeah? We can't treat always all scales completely. Yeah? Okay, so we are always doing a coarse-graining as we move up in hierarchy, and ultimately we reach the process level. So a process model, in my view, is a description how a macrostructure is changing with time, depending on the applied conditions. And this is what you have talked about a lot before, right? You have even you've even gone to the level above that, which is the plant flow sheet, which you can do in HSC, which you can do in SysCAD. Tana is also around, I assume. There are tools for that. And when you do this, you don't want to go into the details of what's really happening in the process, maybe at all times. Yeah, you want to have a coarse graining that is reasonable, that is useful. Again. Okay, now, what do you really need if you want to model the time evolution of macrostructure depending on the applied conditions? You need to describe transport and reaction. And I have separated here two different areas. There's all the part above microstructure to macrostructure, where I would say some aspects are extremely relevant that have to be modeled. And then there is the other part, which is hierarchically lower than that, which is on the atom assemblage to phase assemblage level. And when I put now all of these keywords here, this is not, I'm not pretending that this is complete, but all of these things are things that you usually model on the micro to macro scale. And you have to model on that scale, because otherwise you will not be able to describe the reality. And then you can go to the phase level, the phase assemblage level, the atomic level, and here you have more fundamental properties that you describe. We will see that later with diffusion. We've seen it yesterday in Olina Volkova's talk on viscosity and the change of viscosity as you go from a purely liquid viscosity that is down there to the suspension viscosity that is on the mesoscale level. Yeah? And that is something that you have to consider, you have to take into account. Then we have the reaction side. Again, many aspects that you take into account on the micro scale to macro scale level. And then there are other aspects that you take into account on the phase level. And there's one property that you find which is very, very dear to my heart, and I guess all our hearts, which is the driving forces that show up on both sides. Actually, the only one I think that shows up on both sides, because you need the driving forces for the diffusion, because that is driving your diffusion ultimately, and you need the driving forces for all of the nucleation growth and all the phase transformation, essentially. And this is why I guess you are so happy about using FactSage, using fundamental thermodynamics, because if you don't get the driving forces right, if you ignore driving forces and how they change, you're lost. You're screwed from the start. Okay, now the title of my talk was why is it so difficult? And I think that if you look at the state of the art of metallurgical process models, and you can attack me for that, I think most of the metallurgical process models have some coverage of the meso to sort of microscale, mesoscale, macroscale phenomena that are important to understand transport and reaction. But I think that very, very few are even able to link that down to the effects that are important to describe the phase and atom assemblage dependencies of reaction transport phenomena. And that is a real big problem, my point of view, and that is also what makes it so difficult. It's not easy to do that. And just to give you one example here, no. Before I go to the example, I just want to first go back to the philosophers. Even Rushed, reason interprets nature. Yeah, this was my attempt of interpreting nature and what needs to be done in order to develop process models for metallurgical reactors. We have the Plato, appearance not equal reality, and many models one reality. Yeah, I see the value of the empirical listening to the furnace. That's definitely super helpful, because there are many models. You can describe whatever with some model, but there's only one reality ultimately, and we want to have a model that's able to approximate reality in a way. Okay, and then the 4 whys of Aristotle. The material, the formal, the efficient, and the final cause. And I thought about that. I actually just detected that yesterday when I was doing the fine preparation for today. I thought, okay, that's interesting. What does that mean? So if you read the 4 causes theory by Aristotle, you see that there is the material cause, and that in the context of process modeling is what physics do we include in the model. We will not include all of the physics that has been here as keywords on the slide. Yeah. The formal, how is it represented? Yeah, do we discretize? Do we whatever? How do we solve all of this? There is the efficient. What changes how the model will behave? And that is our input, right? What's the input parameter that we use for a model? And then there is the final. What is the goal of the model? And I think that the final and the material, this is the part where we have made a lot of steps in the DRI case. We'll come to that in a minute. I understood last night that the efficient, what is the input? That is one of the things with which we struggle, because it is so complex. As soon as you go to even something as simple as an iron oxide pellet, this is the part that is hard for us to do. Okay, the final. The final now, I'm just taking a bit away already from Anna's presentation later. The final is we want to have a DRI model that is able to predict the final metallization degree, and whether that will be at 93%, 94%, or 97%. You can see if you take 100% minus that number, that is your iron loss. And you don't want to accept a 93% efficiency in the reduction of an iron oxide ore. Yeah? So this is our final. What is the goal? And if we know that this is our goal, then we can deduce what is the material, what physics do we need to represent. And you see the things that are black here, these are, all of these things are things we're trying to get together. And then we believe we are able to get to the final, at least for a single pellet. We're not yet talking about the upscaling to a furnace reactor. That will be even more difficult. But at least that part. And I think this is a kind of, coming again to the education part, I think it's important to say these things are the things that we cover, and everything that's grayed out are things we ignore because we believe they are not important. We can coarse-grain them away. We can ignore them because they're not super relevant. Again, engineering decision. Yeah. All right. With this, thank you very much for the attention. And if you like to learn more, Anna will talk about this. And I'm here for the breakout session. I love talking about this. So talk to me.
Thank you very, very much, Moritz. Are there any questions? Okay.
This is...
Yes. This time I prepared one. Moritz, if Raphael would have pictured you in the School of Athens, what would be your summary of what your philosophy of materials is?
Oh, dear. Make use of a solid foundation and also know the limits of your solid foundation and then make it easier for others to understand you. I think that is 3 pillars of Moritz.
Thank you. And now we have one.
Thank you for that thought-provoking presentation. So I would ask for everyone here in the room, what is your advice to us young researchers here who have experimental data and trying to understand them by doing FactSage calculations? How do we kind of combine or find some kind of uniformity with all this data? What's your advice for us?
My advice is, if you want to do this, think about your final first. What is your goal when doing this? Yeah? Do you want to understand what's really happening on a lower level? Do you want to predict what would happen if you change your efficient, if you change your input? Yeah? I think these 4 whys, I think being clear on that is super important, because otherwise there's a high risk that you start doing something and you only notice later that you maybe should have done something else, considered something else. And once you have that clear, it becomes much easier to think about this hierarchy that I tried to describe here on the left-hand side, and then think about what are the mechanisms that you have to consider on the different hierarchical levels. And then with what you will get from FactSage is mainly as a user the phase assemblage connection. And sometimes you will notice, there's playing out if I assume an effects. We have transport and reaction here. I'm talking essentially about kinetics, right? And there are things that can go, that can be different in experiment compared to what you would get with FactSage. We would talk about constraints in the afternoon, how you can maybe make use of that. Or maybe even a data coverage problem, and then you would have to go to the atom assemblage to maybe think about database development. Maybe that helps. Thank you.